All right, welcome back, everybody. So we are next going to be finishing up linear regression. We've gone through the overview of what it is, how it works, but we have skipped the mathematics behind gradient descent just a little bit. So we need to do some calculus for that. And then once we develop the calculus for it, we will then move into the actual code, which is going to be surprisingly simple, I think. I think you're going to like the code, so we shall see. Alrighty, so let's go ahead and jump into the mathematics behind this. So we had that the gradient descent algorithm was basically theta 1 gets, or the new theta 1 gets the old theta 1 minus alpha times the partial derivative of the cost function, right? So we had theta 1, and I should probably call this is going to be the new, is equal to theta 1. This is the old theta 1 value, the old guess. Um, so we're going to be updating the new one with the value of the old one minus the alpha times the partial derivative of the cost function. So minus alpha times the partial derivative of the cost function. Okay, so that is the bare bones of what we need to develop. It's actually not that bad, but we've avoided it up to now because we have to use calculus, and specifically we're going to need the chain rule, and we also have to know how to do a partial derivative. So those two things we need to have. Um, so before we jump into that, the actual calculus, let's talk a little bit about partial derivatives. So let's say that I have y is equal to 2xz minus x squared plus z cubed. Okay? Now, if I wanted to take the derivative of y with respect to x, I've got a problem because z is also a variable and it can be changing at the same time that I'm taking the rate of change for x, and so we get a big mess. So to avoid all that, we institute the partial derivative. So if I take the partial derivative, which is that little curly Q, the partial derivative of y with respect to x, well, now we're in business because the second I take the partial derivative, I lock all the other variables as if they were constants. So I hold them fixed. So when I take the partial of y with respect to x, now this z variable is a constant. I treat it just like a constant, 5 or a -7 or something. Alrighty, so if that's the case, the partial of this term right here with respect to x, well, x is the only variable and it's to the first power, so this is just going to be 2z, right? Then I move over to the next term, the partial of this expression with respect to x. So the partial of this term with respect to x is going to be minus 2x. Then I come over here, and z is a constant. There are no x's over here, so it's just the partial derivative of a constant with respect to x, which is 0. So if you wanted to, you could do a plus 0, but most of the time we wouldn't just list this. We'd only list this. Now, if I wanted to do the partial of y with respect to z, now, instead of x being held fixed, z is going to be held fixed. Let me lower the size a little bit of the eraser. So now my x's are constants. Okay? So the partial of this term with respect to z is just going to yield 2x because those are the constants that are multiplied by the z. And then the partial of this term with respect to z, this is a constant, gone. So if you want, you can do a minus 0 there. And then plus the partial of z cubed with respect to z is going to give me 3z squared. So that's how you do a partial derivative. You just treat everything else as if it were a constant. Okay? Not too bad. Now let me clear this, and then we will get started on that. I'll make a large eraser so I don't do too much work. Alrighty. So Now we're going to need to take the partial of the cost function with respect to theta 1. All right? So the cost function that I have down here is j equals 1 over 2m. So I can, there we go, and my eraser on. So j is just equal to 1 over 2m. Now this is times the summation, so I'm going to do all these summations, if you will, and then multiply by 1 over 2m. But when we're talking about the partial derivative, it's even easier. In the code, we're going to have to do that, but in talking about the derivative, it's easier. So this is the summation I from 1 to m. So summation I from 1 to m of, and I'm going to put a bracket here instead of a paren, just because it's kind of really emphasizes that this whole thing is being summed over. So it's going to be theta 1 times x sub I. So theta 1 times x. I know I said sub. It's just going to happen. I'm used to saying sub in mathematics. So the xi, the ith term, oh, that's hard to say, and then minus yi, and then all of that, we're going to have quantity squared. So we have our guess. This right here is our predicted y value. This is the actual y value. And so this is our hypothesis function, right? So this is, you can kind of think of this as y hat, and this is y right here. And so we're going to be looking at taking the partial derivative of this with respect to theta 1. Okay? So I'm going to write that out. Partial of theta 1, big bracket, 1 over 2m, summation I from 1 to m, bracket right there, theta 1 xi minus yi, quantity squared. Okay? So the partial of all this with respect to theta 1. So first thing, I can take this 1 over 2m completely out because it's not dependent on anything. It's just a constant. So 1 over 2m times, I've got this summation here, but this summation is summing over I. It has nothing to do with this partial, so I can really move the partial on the inside. So I equals 1 to m partial with respect to theta 1 of, now for the fun part, I've got theta 1 times xi minus yi quantity squared, like that. Okay? So the way that I'm going to handle this is I'm going to use the chain rule for this, where I'm doing the derivative of something that isn't the plain old variable. So I take the derivative of that something, and then it has to, where the interior, how to say this? Well, I just messed that one up. When I'm taking the derivative of f of g of x, it's the derivative of the exterior, interior untouched, times the derivative of the interior, right? That's the chain rule. Well, same thing's going to happen here because this is a power right here, but inside here is just not theta 1, it is a bunch of other stuff. So I need to do the power rule of the chain rule, and I'm going to get, here we go, 1 over 2m summation I from 1 to m of, okay, this becomes the derivative of the exterior with the interior untouched. So the power rule is going to kick in for the exterior. So this is going to be 2 times theta 1 times xi minus yi to the first power. That takes care of this derivative of the outer, but the interior is untouched. Now I have to multiply it by the derivative of the interior. Well, the derivative of this with respect to theta 1 is just xi. So times xi. And this is what I've been waiting for. Now, for those of you who have been wondering, why in the world we've been doing this 1 over 2m instead of 1 over m? I said it made the math easier. It's so that we can do this. That's it. That's what it's there for. So if you will allow me, I'm going to erase this part right here for just now, and then I will take a step back and we'll erase everything in just a second. First off, I want to put this down. So my new, why is my pen not working? My pen just stopped working. What's going on? Why are you not working? That's weird. I have no idea. My pen has decided to suddenly stop working, which is kind of odd. It's the second time today that the pen has just died. All right. Oh, there we go. We're back. That was weird. So now I'm going to update this right here with what we have here. So this is going to be theta 1 gets theta 1 minus alpha times big bracket 1 over m summation I from 1 to m of theta 1 times xi minus yi times xi. And that is finally the partial of j with respect to theta 1. So this is what we're going to need to code in when we get down to the part where we do the gradient descent. We need this line right here. Alrighty? It's really not bad to code. But that's it. This is what we have to have right here. Let me box it in. I'll even use a different color. This is the last piece we need for gradient descent. Okay? So, gradient descent. Alrighty. So, good deal. Let's go ahead and switch over to our code. Let's see, where is that located? Right there. Give me a second, I have to change that. Okay, see if this works. All right, hadn't switched over yet. There we go, magic. Okay, so we're now going to code this up from scratch. I'm not going to pretend to be doing this totally from scratch. I'm just going to code it in using a reference I've already coded that I know works. But I promise I wrote that from scratch. I didn't pull that from anywhere. So let me go to the last slide before we do that, because there's something I want to say about Python before we jump in. Python is, in my opinion, the most readable of all the computer languages that I've coded in. A lot of it looks like English. It really does flow well. But there are some peculiarities to Python that are going to give you lots of trouble until you get used to them. By far, the number one thing that gets people in trouble with Python is indenting. So Python doesn't make blocks of code blocks by using any kind of symbols. It just assumes that everything that is indented a certain amount is all part of the same block. So that means it's really readable. If I actually look at it and start reading it, it's extremely readable. Like, it looks like English. Well, English. But you get in trouble really easily, because if you have a single space where you're spacing things over, your program is going to blow up, or worse, it'll run, but it won't do what you want it to do. So let me show you what I'm talking about. Um, let me go to Spider. Alrighty. So if I had something like this, um, for let's actually, there's none of that for I have no idea, sample colon. Second I put that colon there, I'm telling it that I want it to be a block. A block of code is following this. And so every time there's a value in sample that I'm pulling out, don't worry about that. It's going to execute this block. So notice it's spaced over automatically for me. So print hi, that's one thing. X gets X plus 1. Okay. Uh, Y gets 90. I have no idea. But if I do print X, well, that would be the actual, let me actually do the non-string version. Alrighty, so this right here, this little sample bit of code, when you put the colon after one of your control statements, like a while loop, a for loop, an if statement, things like that, everything that is indented is executed as part of a block. The second that there is not an indentation there, it doesn't treat that as part of the block. At no time did I put a symbol in here whatsoever. Python just automatically looks for that indentation. So that is by far the worst mistake that beginning Python coders make. If you're used to doing something in C, you might be thinking, you have to put like a curly brace here and a curly brace at the end of the block, stuff like that. Python doesn't do any of that. Python literally looks for indentation only. So yeah, have fun with that. That is the only thing that I love now that I'm used to it, but I could not stand when I first started coding in Python. That was by far my favorite pet peeve. So anyways, let's start off with, we're going to code our linear regression from scratch. We're going to start off with just 3 points, 3 data points. I'm going to call them, it doesn't really matter. Let's go with data points. Gets, and now let's define them. So we're going to do 1, 1, and then maybe 2, 2, and 3, 3. That's what we were talking about before, right, in the example. So I already know what the best slope should be. The best slope that fits that set of points is a slope of 1. So it'll give me a built-in check. Alrighty, so now let's go with an initialization for theta 1. So theta 1 gets 0.0. Just initializing it to have a value of 0. Alrighty, alpha, we need to initialize that. Let's start off with 0.1. Like I said, that is a good generic alpha. And how do I know that? Experience. It's small enough to generally converge, but it's large enough that it doesn't take a long time. You'll see as we try to break the code at the end, it's easy to break the code if you don't have the right alpha. All we have to do is just have the wrong alpha and our code is going to break all over the place. So that's okay. So we're going to say we have M number of, or M is the number of training examples that we're going to be using, and we're going to be summing from 1 to M. So let's say M gets the length of the data points. Okay? So M, the length of the data points, is the number of items inside this list. There are 3 items inside the list, so M is going to get 3, the value of 3. Alrighty? So here we go. We're going to say the X value is 0.0. The Y value is 0.0. And we're going to start initializing a few things. So the count is going to hold the number of times that we're going to go through the gradient descent part of the algorithm, how many times we loop through to try to get a better and better guess. So count is going to start off at 0, and it's going to be an integer because it's going to hold the number of times we've looped through the loop, which kind of makes sense. Max iterations. So you can put this whatever you want. I always like to include a maximum number of times I want it to cycle, just so it doesn't get stuck in an infinite loop. We'll go with 50,000, but you can make it half a, I don't know what that was, 50,000. Good. Alrighty. You can make it whatever. Even 10 billion still wouldn't take that long. Okay, 10 billion might, but 10 million sure wouldn't. Alrighty. Then we're going to have our sigma. So sigma is going to be a variable that is going to hold the summation of each of those data points as we take the hypothesis function minus the y value. Okay, so the theta 1x minus the y. And then it has to be multiplied by the x. That was what we found with our gradient descent algorithm when we did the partial derivative. So sigma is going to hold that, and so it needs to be a real number, so it's a decimal, like that. And then as we loop through, we are going to want to compare our guess for the new theta 1 with the value for the old theta 1, because as we saw with the gradient descent algorithm, as it nears the best possible answer, the slope gets closer and closer and closer to 0 at the bottom of the parabola, so that it winds up doing very little change to theta 1, and at that point we want the program to stop. So the diff is just going to hold the difference between the old theta and the new theta. So diff, we're going to give it a value that's not 0 for a reason. We'll give it a value of 1 because we want to have a variable called tolerance. And that's going to have how close we want the two values to be before it exits the program. So maybe we want to make it 1/100,000th. Is that what that is? Something like that? That's fine. Doesn't matter what we make it, just something small. Alrighty. So all of this has just been initializing things. Now let's actually get to the code. Here we go. So what we want it to do, we want this program to run and loop through gradient descent over and over and over until one of two conditions is met. Either the difference between the old theta 1 and the new theta 1 is less than the tolerance, which means it's close enough to kick out, or the count has exceeded the maximum times we want it to loop, our max iterations. So we're going to write this, it's going to be close to English, so while diff is greater than tolerance and count is less than max iterations, colon. Now we're going to have a block of code. Alrighty? So this is going to execute the following code over and over until either the difference is less than or equal to the tolerance or the count is equal or greater than the max number of iterations. So let's see what we're going to do in here. Well, what we're going to do is look at the points inside these data points. So for point in data points, so what this is going to do is it's going to pull out the points one by one. This is one of my favorite things about Python. It looks this right here, this for point in data points. It looks inside the data points variable and starts pulling out the individual pieces. It stores those pieces one at a time in the variable point. So it stores it in point. It takes the first one out, stores it in the variable point, does all the block of code that we're about to type in. When it finishes with that, it then moves to the next point and does the same thing. And then it moves to the next point. And it keeps doing that until it goes through all of the items that are inside data points. which is just amazing. Such a nice feature. So what we're going to do is we're going to say x is going to get the x value of the point. So if you look right here, we have for each of these points inside data points, we have we have two values, right? We have a, if I change this, that might be easier to see. The 1 right here is the first thing that's inside that point, and the 5 is the second value that's inside point. So to access the first value, I do bracket 0. Bracket 0 says I want the first item in the list because in Python, all of our references to items inside of a list, you can think of items inside of an array, start at 0. So the first item is 0, second item is 1, third item is 2, etc., and it goes all the way up. So this takes the first value that's in the first point, because it starts off with the first point, and stores that in the x, which is what we want. We want it to have this value right here. Okay? So x is going to get that value, and y is going to get the second value. Okay? Just like that. Now, sigma is going to get, remember, sigma is supposed to hold the summations. So sigma plus, here we go. We're going to have theta 1 times x, let me space that out a little bit, times x, and then we're going to have minus y, and then times x. Oops, x like that. So sigma starts out at 0, and then it's going to add to that theta 1 times x, that is my hypothesis function, minus y, times the x. This is that piece that we got when we took the derivative, the partial derivative of the cost function. This is what is inside of that summation. That's all this is. And so what it does is it runs through each of the points and adds the values that it gets from the calculation to sigma. So it is actually performing a summation. So that's kind of nice. Now, that's all I want it to do for each of the points, is to run through the points inside the data points and get all those values. Once it has that summation, now I can say, I can come down here and not do a indentation. I can say let's see, I need a variable here, something to hold the old theta 1 value. Let's see, I forgot to call, let me try new theta up here. New theta 1, 0.0. I forgot I needed a variable to hold all this. So I come down here, I'm going to say new theta 1 gets the old theta 1, which we're just calling theta 1. Probably should call it old theta 1, but theta 1. Alrighty, minus alpha times 1 divided by m times sigma. And that is what we had for the rest of the gradient descent, right? Old theta 1 gets the new theta 1 minus alpha times 1 over m times the summation. The summation has been stored here in the sigma variable, so that's it right there. So it's alpha times 1 over m times that summation. Boom. Alrighty? So that is the gradient descent, but now we need to check and see if it's close enough. So the diff that we're going to be looking at gets, we're going to do the absolute value of the new theta 1 minus theta 1, okay? And then we're going to say theta 1. Now that we've stored the difference, we can now assign the new theta to the old theta. So theta 1 gets new theta 1. We also need to reset sigma because the next time we iterate through gradient descent, we need to start over with the sigma equal to 0. So sigma gets 0, 0.0. And last one, we need to increment the count. So count gets count plus 1. Alrighty? Now, that's it. That is the entire code for the linear regression. It's going to check to see if the difference is still greater than the tolerance. If it is, it's going to it's going to keep looping. It's also going to check to make sure that the count is less than the max number of iterations. This is where it does the summation part right here, this little piece, and it goes through every point, adds that value, that x times y, theta 1 times x minus y times x. It does that summation here. Then it does new theta 1 gets the old theta minus alpha times 1 over m times that sigma. And then it just stores the difference, resets the theta 1 to the new theta 1. And then when it gets to the end of all this, it will now check to see if the difference is greater than tolerance and count is less than max iterations. So the last thing I'm going to do here is add an output statement. So print, let's see, what do we want to say here? The slope of the line that best fits the data is, okay, let's go with theta 1. That's where it will be stored. Okay, and then below, let's also see how many iterations it took. Print the number of iterations needed was, okay, and then we'll do that. We'll put count for that. Okay, that's it. That's everything. That is the entire program right now. So now we can come up here and press the green arrow and run it, see if it runs. Fingers crossed. What do you know? The slope line that best fits the data is 0.99999. It's basically 1. And it took 19 iterations to get close enough to where the tolerance, it actually exceeded the tolerance that we wanted. That's it. That's how it works. Now, let's play around with our alpha just a little bit to see what happens. So if I look at my alpha, it's 0.1 now. What if I make it, oh, I don't know, 5? What's going to happen? Well, let's see. The slope of the line that best fits the data is nan. Nan stands for not a number. Usually it blew up to infinity. It only took 230 times to blow up to infinity as well. Not really infinity, but it was more than what it could handle as far as the size of the number was larger. So what happened? Well, what happened was, if you remember, we have the parabola. If alpha is too big, it starts to bounce out of the parabola instead of gradually descend down towards the bottom of the parabola. So that's what happens with a large alpha. It literally bounces out of the parabola. What if I make alpha really small? What if I make it 0.00001? Will that work? Well, let's see. Let's run that one. So, turns out if you have too small of an alpha, you're going to get in some trouble when you're subtracting the new theta and the old theta. This one, it said it didn't exceed the number of iterations, but this is definitely not the correct value. Let me pull it in just a little bit. You should always have your alpha be smaller than, or bigger rather, than the tolerance itself that you're trying to approach. Otherwise, it doesn't make any sense. Let me do 0, 0, 1 and run that. Now it works. Okay, so it found that the slope is basically 1, but it took 1,315 tries compared to 19. So what's going on there? A small alpha will generally work, but it takes a very long time to converge versus an alpha that's kind of in the middle. Um, we can also play around with this and maybe make it 0.4. See how fast it converges then. It did converge. It needed a few more. That tells me that it was hopping down at the bottom. Okay. But what if I do 0.3? What are we going to see? There we go. At 0.1, we took 19 tries. 0.3, we took 14. I'm betting 0.2 is going to be somewhere in the middle. Maybe. Oh, 0.2 hit it dead on. 6. Wow, that was incredible. That means as it was hopping, it just happened to hop straight down into the minimum or something really close to the minimum, like that. Um, so your alpha is nothing but experience. That's all it is. Sometimes it is very easy to figure out what it should be. Sometimes it takes a while, but it is. You can even run programs that will determine the appropriate alpha, or at least a good, starting value. But for what we're going to do this semester, we'll choose an alpha that is, it makes sense based on the data that we're working with. And 0.1 is almost always a good place to start. This is not just alpha 2, this is our step size, our learning rate. So every time we're doing something that requires learning, training, we need to set something in there. That's what we're going to be working with. It's going to be this alpha. Now, in the things coming up, we're not always going to have the code where we're doing everything by scratch. We're going to be calling libraries that automatically handle that for us. But even then, behind the scenes, alpha is being chosen, and it's being chosen based on the data. So there you go. Alrighty. I hope that you've enjoyed this little walk through Python. If you look at it, all of this stuff up here was just initializing things. The actual gradient descent is right here. This handles the summation. This handles the actual gradient descent part. The theta 1 is theta 1 minus alpha times the partial derivative stuff. So that's it. I hope you enjoyed it and also notice how easy this is to read. The for loop here has this stuff in it. The while loop has all of this stuff in it. It's so easy to read. Love the way Python indents. Alrighty, that's everything. I will be sending this video out and posting the code so you can download it and play around with it yourself. Look for a homework in the next little bit. I need to come up with one that's interesting for y'all so y'all can use this code to actually tackle the homework, and I think that'll be it. Alrighty, y'all have a good one, and I will see you later. Bye, everyone.